Launched in the 1970s to explore the outer planets, the Voyager probes went far beyond their original mission. They crossed the boundary of the solar system and entered interstellar space, revealing a high-energy transitional zone unknown to science. This is the story of our first steps beyond the sun's reach, toward the true edge of the solar system. After more than 4 decades of traversing the vastness of space, NASA's legendary Voyager probes have crossed the boundary of the heliosphere, the invisible frontier where the charged particles of the solar wind are halted by the interstellar medium. At this threshold, onboard instruments recorded a startling phenomenon. The temperature of the surrounding environment soared to 50,000 Kelvin, comparable to the surface of a white dwarf star. This is not a physical wall in the conventional sense. Rather, the heliopause is a turbulent transition zone where charged solar particles collide violently with interstellar matter, forming a sheath of superheated plasma that envelops our solar system. How did the Voyager spacecraft, built in the 1970s, survive such extreme conditions? And how do these revelations transform our understanding of the sun's shape and the true extent of its influence? Join us as we unravel the extraordinary journey of humanity's first interstellar emissaries and explore the mystery of the invisible fire belt that defines the final frontier of our planetary system. Our solar system does not simply end at the outer orbits of the planets. In truth, it extends much farther, shaped by an immense invisible bubble known as the heliosphere. This dynamic structure is created by the solar wind, a stream of charged plasma particles constantly emitted from the sun's surface, carrying magnetic fields and energy outward. But as these particles push into interstellar space, they gradually lose momentum, colliding with a frigid vacuum filled with gas and dust, remnants of long-dead stars. The boundary where these two realms converge is known as the heliopause. It marks the end of the sun's direct influence. Crossing the heliopause is no trivial feat. Yet Voyager 1 and Voyager 2 have done precisely that, becoming the first human-made objects to enter interstellar space, a milestone that forever reshaped our understanding of the cosmos. In August 2012, Voyager 1 made history by becoming the first human-made object to cross the heliopause, the boundary where the influence of the solar wind gives way to interstellar space. 6 years later, in November 2018, Voyager 2 achieved the same milestone, though at a different location. Remarkably, despite their separation, Voyager 1 being nearly 18 billion kilometers from Earth, both spacecraft recorded strikingly similar data, unveiling common patterns in this mysterious transitional region. As they exited the heliosphere, both Voyagers detected a dramatic spike in particle temperature, reaching as high as 50,000 Kelvin. It is important to note that the onboard instruments do not measure temperature in the traditional sense. Instead, they infer it from the energy of particles present in the environment. This region is often referred to as a firewall, though the term can be misleading. There is no literal wall or flame. Rather, it reflects a sudden increase in thermal energy within a narrow boundary zone, where the solar wind slows, compresses, and is confronted by the opposing flow of interstellar matter. These discoveries not only open a new window into the exploration of interstellar space, but they also lay the groundwork for a deeper understanding of how our solar system interacts with the broader galactic environment. One of the most significant revelations is that the heliosphere is not static. It is not a fixed border, but a flexible, shifting boundary that expands and contracts depending on the sun's activity. During solar maximum, the sun emits more powerful solar winds, pushing the boundary outward. During periods of solar minimum, the heliosphere retracts inward, and while the region exhibits extreme temperatures, the spacecraft remain largely unaffected. This is because the particle density here is exceedingly sparse. Even at tens of thousands of degrees, there are too few particles per cubic centimeter to effectively transfer heat to the spacecraft. It is a realm of extraordinary extremes, hot yet nearly empty. The heliopause is a region of extreme physical phenomena, a dynamic frontier where charged particles from the sun collide with the interstellar medium. But what exactly creates such high-energy conditions? The answer lies in the complex interplay between plasma and magnetic fields. As fast-moving solar particles encounter the denser interstellar environment, they cannot pass through easily. Instead, pressure builds, magnetic fields become compressed, and in some cases, a process known as magnetic reconnection occurs. This phenomenon, where broken magnetic field lines realign and snap back together, releases sudden bursts of energy. The result? The formation of collisionless shock waves, a unique mechanism for particle acceleration. Unlike shock waves in Earth's atmosphere, where molecular collisions dominate, here the heating and acceleration of particles are driven by electromagnetic forces. Charged particles, even when separated by vast distances, interact through their electric and magnetic fields, creating collective effects that unleash tremendous amounts of energy. This phenomenon not only sheds light on plasma dynamics within our solar system, but also offers a new perspective on astrophysical processes on a far grander scale. One of the most surprising discoveries from the Voyager mission was the unexpected alignment between the magnetic field outside the heliosphere and the one within. This finding directly contradicts earlier models, which had predicted that the interstellar magnetic field would overpower and alter the direction of the solar magnetic field at the boundary. Initially, scientists considered Voyager 1's data to be a curious anomaly, but when Voyager 2 reported the same phenomenon, all previous assumptions were overturned. Strangely, two magnetic fields, originating from entirely different sources and separated by billions of kilometers, appeared to be part of a single, continuous structure. This discovery suggests that the Sun's magnetic field may be interacting with the galactic environment in ways far more profound than previously imagined. It also raises a critical question. Have our current models of solar-wind interaction with the interstellar medium truly captured the full picture? The heliosphere is not merely a physical boundary. It serves as an invisible shield, protecting the solar system from high-energy cosmic rays. The stronger and more expansive this heliospheric bubble becomes, the more effectively it deflects harmful particles, reducing risks for satellites, astronauts, and even Earth's atmosphere itself. Understanding the mechanisms that govern this boundary not only helps us predict long-term changes in the space environment around our solar system, but also opens a new window into how other stars might interact with the interstellar medium. What Voyager has uncovered has not only transformed our understanding of the solar system, it has challenged long-standing astronomical models once considered standard. And this may be just the beginning. Far from simply identifying a border, the Voyager spacecraft revealed that the outer edge of our solar system is a dynamic, evolving region, far more complex and active than scientists once imagined. These discoveries have not only redefined our knowledge of the heliosphere, but also raised new questions across multiple domains of space science. Voyager's data revealed that the heliopause is not a rigid wall. It can expand or contract dramatically depending on the Sun's activity cycle. This implies that the Sun's sphere of influence fluctuates over time, potentially affecting the levels of cosmic radiation near Earth, not just over decades, but across centuries or even millennia. If this is true, it could help explain long-term changes in the radiation environment of space, with potential consequences for Earth's climate and the evolution of life itself. Though the Voyagers have officially exited the heliosphere, they have not entered a calm, inert space. Instead, they continue to record unexpected variations, from plasma density shifts and magnetic field oscillations to sudden changes in cosmic ray intensity. This suggests that interstellar space is far from homogeneous. It harbors unanticipated structures, possibly shock waves, faint transitional boundaries, or even magnetic buffer zones yet to be discovered. What the Voyagers have uncovered does more than challenge existing models. It paints an entirely new portrait of the interaction between our solar system and the galaxy. It is a portrait that is dynamic and full of surprises. As these two probes continue their voyage into the dark expanse of interstellar space, each signal they transmit may carry clues to even greater mysteries: how stars shape the space around them, and perhaps even the origins of the interstellar medium itself. Though built to endure, the Voyager spacecraft are gradually running out of power. The energy supplied by their radioisotope thermoelectric generators is slowly diminishing with time. By the early 2030s, both spacecraft may cease to function. Yet their journey does not truly end there. The scientific legacy they leave behind will echo through the centuries. To continue the mission, NASA has prepared a new generation of exploration, the Interstellar Mapping and Acceleration Probe, scheduled for launch in 2025. Unlike Voyager, this probe will not leave the solar system. Instead, it is designed for a more focused task, mapping the boundary of the heliosphere by detecting high-energy particles that travel backward from the edge of the solar system. The data gathered by this probe will enable scientists to form a more complete picture of the heliosphere's shape and structure, while tracking its changes over time. It marks a major step forward in humanity's ongoing journey to understand the cosmos. In parallel with ongoing missions, pioneering projects such as the Interstellar Mapping and Acceleration Probe are set to embark on a bold journey, aiming to reach a distance of 1,000 astronomical units from the Sun. This distance is more than 20 times farther than Pluto's orbit. The mission's objective is to venture beyond the heliopause and deliver a sharper, more detailed portrait of the interstellar medium. How it operates, what its structure looks like, and whether even deeper, unknown boundaries exist beyond what we've observed. Voyager has provided the first data points, mere dots at the edge of a vast cosmic map. But to piece together the complete picture of the solar system's final frontier will take decades more, along with future missions equipped with far-reaching vision. Thanks to the discoveries of the Voyager spacecraft, we now know that the boundary between our solar system and interstellar space is not a passive threshold. It is an extraordinarily active region, reaching temperatures of up to 50,000 Kelvin and shaped by complex magnetic interactions. This revelation of such a dynamic, energetic environment has upended many previous assumptions and offers a rare glimpse into the process of transition, from the Sun's sphere of influence into the vast realm of the galaxy, where the greatest cosmic mysteries still await discovery. The Voyager probes may soon fall silent, but their legacy endures. Their discoveries reshaped how we see the solar system and our place within it. As new missions prepare to journey farther, deeper into the galaxy, Voyager stands as proof that even the smallest signals from the edge of space can carry answers to the biggest questions we have ever asked.